So we're in a situation where we've done a nonlinear regression on a set of data here with 16 observations. And we've been using this model here and then the method of least squares. Note that down. To find the best fit, that is the best value or the optimal value of these two parameters, beta naught and beta, well, I guess that should be beta 1 actually. So I'll just change that. Beta naught and beta 1. Right. And let's say we found, using numerical solution, we found values of roughly 238 and roughly 0.0005. So what we want to do now is we want to find confidence intervals for these two parameters, because we know that if we did this experiment over again with another 16 observations or whatever, then we would be bound to find some other values of these parameters. So what is really the confidence, let's say 95% confidence interval of these parameters? How do we do it? Well, if it were in linear regression, this is nonlinear regression, but if it were in linear regression, so I'll just do a quick recap of that. Linear regression, I'll just remind you how we find the confidence interval of the parameters there. What we would do is that we would define what we call the design matrix. Design matrix. And that would contain a column of ones all the way down 16 rows if we have 16 observations, and then a column of the x values, x1, x2, x16. And if it were in multiple linear regression, we would have another column of x2 values and x3 values and so on. In this case, we only have one column of x values because it's just simple linear regression that I'm talking about here. And what we would do then is that we would transpose this matrix, multiply it by itself, and invert the result. And then we would multiply that matrix, and by the way, this would be a in our case here, it would be a 2 by 2 matrix because we have two parameters in our model. But in general, it would be a p by p matrix where p is a number of parameters. Right, so we'll take this matrix and multiply it by our variance estimate, one we usually call sigma hat squared. And the variance estimate, just to recap, well, that's just the sum squared error divided by n minus p, where n is the number of observations, in our case 16, and p is the number of parameters, in our case 2. So this is our sigma hat square, just to remind you. And the sum square error, just to remind you what that is, that's all these areas corresponding to the residuals in our model. So take the distance from an observation to the predicted on the curve here, the predicted point here and the observed point, and we square that distance, so you get an area corresponding to this square here and this, and all of these we add them up, and then we get the sum of squared errors. So that's our variance estimate, and we'll multiply that number by this matrix here, and what we get is of course a matrix, and in the diagonal we would find, or maybe I should make it a little greater, the variance of beta naught, the variance of beta 1, and if I had more parameters I would have a greater matrix and I would get all the other variances of the parameters. Right, so once I have the variance of the parameters, I can easily find the standard error of, say, beta naught. That's just the square root of the variance of beta naught, so on. And then I'm able to find the 95% confidence interval of the beta naught parameter. That's just beta naught itself plus minus the 0.975 t quantile with 16 minus 2 degrees of freedom. Again, 16 because we have 16 observations and we have 2 parameters, beta naught and beta 1. And then multiply it by the standard error of beta naught, which I found here. So that's what we would do if it were linear regression. The good news is that it's almost the same thing we do in nonlinear regression. I'll just include this one here, like that. In nonlinear regression, let's change the color. It turns out we shouldn't define a design matrix like this. Instead, we need to define a Jacobian matrix. And the Jacobian matrix is defined so that the first column of this matrix is our model, and I'll just call the model here f of beta, right? So this is a function, well, it's a function of x, but it's certainly also a function of beta, beta naught, and beta 1 in our case here. We have 2 betas here. So we take the derivative of the function with respect to beta naught, and we evaluate this derivative at x1. So that's the first element of this matrix. The next row, I take the derivative of my model with respect to beta naught, evaluated at x2. So that corresponds to the next observation here. And I keep doing that for as many observations I have until I get to the last one, x. In our case, that would be x16. Next column, well, you guessed it, I derive my function with respect to beta 1 and evaluate that derivative at x1. And over here, I evaluate it at x2 and so on, and until I reach the final row where I evaluate it with at x16. And that's my Jacobian matrix. So that's a matrix of numbers, and it replaces the design matrix. It takes the same part, it plays the same part as the design matrix. And then I just transpose it, multiply it by itself, take the inverse and multiply it by the variance estimate, and then I get a matrix, just like for the linear case, in which I have the variance of beta naught, variance of beta 1, and so on. So it's exactly the same procedure, except that I don't use a design matrix like this, I use a Jacobian matrix. And if you look at it, this design matrix is actually a Jacobian matrix for the special case when the model is a linear model. So the Jacobian matrix is in fact the one we always use, but in the linear case, it just happens to look like this. It's a simpler appearance, you could say. So let's try to do it in Excel. So here we are with an example of monomolecular adsorption. The X value is the pressure of a monomolecular gas, and the Y values is the absorbed volume by some surface. And we believe there to be a relationship between these two variables, which is given by this model up here. And I should probably change it from Danish into English. So it should be the exponential here. So beta naught times 1 minus the exponential of minus beta 1 times x. And we used the method of least squares and solved it using the Excel solver and found these two optimal values for beta naught and beta 1. Okay, by minimizing this sum of squared error number here. If you don't know what I'm talking about, you can look in another video in which I demonstrate the method of least squares. Right, so what we want to do now is to compute the Jacobian matrix. And in the first column of this matrix, I want df d beta 1, sorry, beta naught. So I have to find out what is that. So if I look at my model here, I need to differentiate this with respect to beta naught. I get it. That's actually quite easy because I just have beta naught times some constant here. So the result is 1 minus the exponential of minus beta 1 times x. And the next column, I have to differentiate with respect to beta 1. That's a little more complicated, but if you look at it for a while, you'll see that you get beta naught times x times the exponential of minus beta 1 times x. So this is my model here differentiated with respect to beta 1. Right. So now I want numbers. So here so this is actually the first element of my Jacobian matrix that I'm computing now. So it's 1 minus the exponential. In Danish, that's a EKSP. EXP, I believe in English. 1 minus the exponential of minus beta 1. And beta 1 is this number here, according to my result here, multiplied by x, and that should be the first x here in my data here, because it's the first row of the Jacobian, like that. And I want to copy this all the way down, so I want to fix this cell here, because that's going to be the same number every time, like that. And then I just copy it to, I don't know how many times, we'll just, obviously too many, I'll just remove those, like that. So that's the first column of my Jacobian matrix. Over here, the formula is different. So it's beta naught, that number here, times x, which is the first x here, times the exponential of minus beta 1 times x, like that. And again, I want to use the same numbers over and over when I copy this, so I'll just fix the cell reference here, like that. There. And then I copy this cell all the way down, like that. And what happens when I copy is that I evaluate this derivative here at x1, and here it's x2, you see the cell C5, x3, so that should be C6 here, and so on. So this is actually my Jacobian matrix. Now, if you remember, think back, what we needed to do is to transpose that and multiply it by itself and then invert the result and then multiply by the variance estimate. Maybe we should find the variance estimate first. So I'll just call it sigma hat squared. And as I said, the variance estimate is the sum square error, which I have here, divided by the number of observations 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 14 observations here, and I have to subtract 2 because I've used the observations twice in order to estimate the two parameters here. So this is my variance estimate. So that's nice to have. And then I'm ready to compute. Maybe I should write it here. The Jacobian transposed, multiplied by itself, and then inverted. I'll just add a bracket here, like that. That's what I'm computing here. And as I said before, this is going to be a 2 by 2 matrix. It was with the x's, but it's the same for the Jacobians here. This is a 2 by 2 matrix. In general, a p by p matrix. So I'll make room for that here by selecting these 2 by 2 area here, and then I'll write the formula. M product in Danish, M mult in English, I believe, MMULT. And then I transponer in Danish, the matrix. And the matrix is this thing here, like that. And we'll multiply it by itself, like that. And I need to invert everything here. In Danish, M invert, like that. And very important, you have to press Control Shift Enter to get the computation here. So that's our matrix, and we need to multiply this element by our variance estimate to get the variance of beta naught. So I'll write here variance of beta naught. Well, that's the variance estimate times this element here, the first diagonal element. And the variance of beta 1 is the variance estimate times the second diagonal element here. That's very small. And then we are ready to compute the confidence interval. Maybe we should compute the standard error of beta naught. Well, that's just the square root of the variance. And the standard error of beta 1, that's the square root of the variance. Right. So 95% confidence interval for beta naught. We'll do the lower bound first. So we take beta naught, subtract the t quantile, t inverse 0.975, and then 14 minus 2 degrees of freedom times the standard error, which is this one here, of beta naught. Enter. So that's the lower bound, and the upper bound is then almost the same, so I'll just copy this formula here and place it here. and change the minus into a plus, like that. So what we can say is that with 95% confidence, the value of beta naught is in between 233 and 244. You can do the same thing for beta 1, exactly the same calculations here.